I'm monitoring the chat line. I'll send the.
She's watching YouTube, but she's not watching.
Oh yeah, I can monitor YouTube as well.
Good evening, everyone. Welcome back. It is our February Speakers Night for 2025. Welcome to RASC Toronto Centre. We are online tonight, and I am Dr. Elena Hyde, the second Vice President of RASC Toronto Centre. This is our Speakers Night presentation. So please note this meeting is an online only presentation and not at our new York University meetup location. Our somewhat new President Scott Masterton will be talking about various programs later on this evening. But first, as per usual, we have a special event to actually kick off here. So I'm going to start off with a land acknowledgement. Like to acknowledge that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. So for today's talk, we have a whole different kind of Earth or planets to get into, and I'm really quite pleased to be able to introduce our speaker, Aiden Weatherbee. He's a space engineering student at York University, and he's done a lot of different research in exoplanets and CubeSats and balloon satellites, robotics and robotics vision systems in particular, and most recently, in the exoplanet regime, he's developed some tools for analyzing what are called exoplanet transits. And of course, I will let him tell you all about that. Um, and of course, Aiden, I have to give full transparency, has also built some wonderful tools for the Alan I. Carswell Observatory at York University, and I suppose you'd say, excellent self motivation actually has resulted in some finished code tutorials that will be executable via cloud computing platforms for all the future students up there. So it's very exciting. I'm sure I'm not the only one who's looking forward to hearing more about these exotic exoplanets. So Aiden, can you please go ahead and take us up, up, and away?
Yeah, thanks for inviting me, Elena. So, as the title suggests, this speech is going to be all about exoplanets, and I've given it this title and image to highlight the amazing discoveries that the James Webb Space Telescope has brought to the field. So, more specifically, I'm going to give everyone a brief history of exoplanet science for some context. I'll talk about how James Webb has impacted the field. I'll go into what gives it these advantages to make it a game changer for us exoplanet scientists. And I'll talk about some of the methods we use to study these worlds and what James Webb has told us thus far. And lastly, I'll end us off with talking about what ground-based observatories like the Alan I. Carswell Observatory or even smaller personal telescopes can do to contribute. So, for some very brief context, the first exoplanet around a sun-like star was only found in just 1995, and this was a hot Jupiter called 51 Pegasi b, with hot Jupiter meaning a gas giant like Jupiter that's orbiting much closer to a star, meaning it's much hotter. So, just 30 years later, we have confirmed over 5,800 more exoplanets of all different kinds. With James Webb, we are slowly moving from just detecting these planets to being able to actually characterize them, meaning understanding things like their density, their temperature, or even their atmospheric composition. So, out of these 5,800 planets found, roughly 80% have been found through the transit method, which I'll go into a bit more later, but it involves monitoring a star for periodic dips in brightness. Now, two key things I want you to know for now is that one, only about 0.5% of exoplanets are expected to transit, and we can only find exoplanets in our own Milky Way galaxy with this method. So, even though we've found thousands, there are expected to be many, many more in our galaxy alone. So I'm sure you all know how great James Webb is, but what makes it so great for exoplanet science? Well, the first thing is the same as every field of astronomy, its aperture being by far the largest we have ever sent to space. So since it was so large, with about 25 square meters in size, it had to be packed up, unfolded, and aligned in space. Now this alignment required ultra-precise actuators that actually allow step size under 10 nanometers. So to give you an idea of how precise this is, if you look at your fingernail and count to 10, it grows at about 1 nanometer per second. So I've actually brought a replica to demonstrate how this works, and I pointed out there in red where it attaches, but each mirror has 6 of these attached to its backside. So I don't know if you can see this bar here, but as I move these gears ever so slightly, that bar will move up and down very slowly. Now, as that bar moves, it connects to this bar, which actually flexes at that nanometer precision. So as I'm turning this top bar there is moving at that nanometer precision. And now that's what James Webb uses on its backside to be able to align its mirrors so precisely. Um, so if you scaled up this mirror to where it was the size of the USA, each mirror segment would be about the size of Texas, and it would be the equivalent of adjusting these Texas-sized mirror segments with about 1.5-inch step size. So that's pretty crazy if you ask me. Now the second thing that makes James Webb so awesome is how extremely cold it is. So a combination of that massive sun shield, the super cool orbit at the Lagrange 2 point, where it's essentially orbiting nothing, and this cryogenic cooling allowed to reach temperatures as low as negative 265 degrees Celsius. So adding together the largest and most precise mirrors in space with these extremely cold temperatures, this makes it so sensitive that it could actually detect the heat of a bumblebee on the moon if it was on Earth. So for exoplanets, this means detecting the subtle change in a star's brightness as this planet passes with more precision than ever before. So before we get into the details of what James Webb has discovered with these capabilities, I'm going to go over the techniques we use and what information each provides us with. So the main workhorse for finding these transit events has been Kepler and TESS, where Kepler initially studied a small portion of the sky, finding thousands of planets, and it passed this torch on to TESS in 2018. Now TESS is still currently monitoring the whole sky looking for more transit events, and it's found 1,000. What these spacecraft do is essentially take continuous images at a set of stars in hopes of detecting one of these dips in light. Now, when you capture one of these transit events, you can immediately get a measurement of this planet's size based on how much light is blocked, as larger planets will block more light. So although it's mainly used for finding planets, it also gives you an idea of the planet's size in the process. Now, with multiple transits, you then know the orbital period or even the length of 1 year for that exoplanet. So if this time is varying between transits, it can indicate another planet's gravity is actually influencing its orbit and changing this length of time. So this allows for the detection of even multi-planet systems. Now, since we know the length of the year, you can also use Kepler's law to determine how far its orbit is from its host star as well. And since you know how far it orbits, you then have an idea of if it's a cooler or a hotter planet. So just by looking at these dips in brightness, we already have somewhat of an idea of what we're dealing with. Uh, but with highly precise telescopes like James Webb or Hubble, you can even capture the secondary transit. So this occurs when the planet passes behind the star. So your telescope is picking up this small change when the planet's brightness is actually being blocked by the bright star in this case. So it's techniques like this where James Webb's sensitivity is really needed. So using the infrared sensors of James Webb, it allows you to isolate the planet's thermal emission, getting an idea of the temperature. And with the optical wavelengths of a telescope like Hubble, we get an idea of the planet's albedo, meaning how reflective it is. Now this difference is because in the infrared wavelengths of James Webb, it's the planet's thermal emissions that we were primarily measuring, where in the optical wavelengths, we are more measuring the reflection that's coming off of the host star. So another method that we use to study and even find exoplanets is the radial velocity method. In fact, if you recall the first planet around a sun-like star, Pegasi 51b, it was actually found using this method. So I have two different videos here on the screen to explain how it works because it's a bit less intuitive for anyone who doesn't know what spectroscopy is. The idea is that you break the star's light down into its individual colors or wavelengths in the same way that a glass prism hanging in your window would shine a rainbow onto the wall. Now, if these colors, which we call the star's spectrum, are shifting back and forth, this is due to the star wobbling, causing the light to blue shift and red shift as the star goes towards and away from us. We know this must be caused by a large planet orbiting it. In fact, even in our own solar system, Jupiter doesn't quite actually orbit the Sun. In reality, they both orbit a common point that's just above the Sun's surface. So even in our own solar system, where Jupiter is less than 0.1% of the Sun's mass, we can see these effects. Now, one of James Webb's most groundbreaking contributions uses the same technique of spectroscopy, but in this case, it's when the planet is in front of this host star again. So when this transit occurs, you can take spectroscopic images, and if the planet has an atmosphere, then it will block more or less light at different wavelengths depending on its elements. Now, this allows us to get an idea of what element might be in the planet's atmosphere. Now, James Webb's instruments detect these slight changes with more precision than ever before, giving us insights into the exoplanet's atmospheric and makeup. So with James Webb's coronagraph, it also allows us to take some of the most sensitive direct images of exoplanets. So this is an instrument that blocks the star's light. So so you can take an image of only the exoplanet without damaging your camera. This is needed because the star can be more than 1 billion times lighter than the planet. So in these images, use a white star to represent the host star, and the exoplanet is what you're actually seeing. So the unfortunate thing with direct imaging is that they really can't be the same planets we use to study with other techniques. The James Webb need planets that are much closer to their host stars to obtain good spectroscopic data. This is because you need multiple orbits to build up that signal to noise ratio. In one transit, you can't quite get that enough signal to noise ratio for any significant measurements. So this planet is actually a rare case that has only been found and studied using direct imaging, and can't do any of the other techniques on it really. But for the vast majority of planets we find, we have those 5 other tools we can use to characterize exoplanets. So I'm going to walk you through discovery and observations of WASP 39b. This is another hot Jupiter like Pegasi 51b, and there's actually a reason for this. Our technique for finding exoplanets favor large and close orbiting planets heavily. This is because they block way more light and they transit more often, and they cause the star to wobble more due to the closer orbit. So they're easier to find with both of the transit and the radial velocity technique, which those two techniques have found about 90% of the planets combined. So if you take this bias into account, even though we've found mostly hot Jupiters, it's actually the Neptune-sized planets, sub-Neptune-sized planets that are most common in our cosmos. But to start us off, it was found with WASP, or the Wide-Angle Search for Planets Telescope in South Africa, hence the name WASP 39b. I know us astronomers are super creative with our naming. But on the screen, you can see the initial transit. Too much noise to claim it's a planet just yet, but definitely something going on. But even with just this, we can get an idea of how big the planet would be if it is a planet. So now the second thing usually done is follow up radial velocity measurements to get an idea of its mass. And since we know its size from the transit, this also will tell us its density. And these can be done with ground-based observatories like AICO, which is why these two techniques are often done first. In fact, the measurements shown here were taken with just a 1.2 meter telescope, so not that much bigger than AICO. And for planets that don't transit, you can only calculate a minimum mass with this technique. But because this planet also transits, we know it's orbiting in our exact orbital plane, so we know it's the actual mass that we're measuring here. So from this change in speed, the estimated mass is just 0.28 of Jupiter's. So though it's much larger, it's much lighter than Jupiter. So the next thing you'd do would be turn your telescope back to it for a long period of time than just one transit. So this gives us an idea of its orbital period, like I said before, which also tells us the distance it's orbiting from its host star through Kepler's law. So this is where amateur astronomers like us can really contribute. So it takes a lot of resources to track 5,800 planets in the long term to capture any changes in orbital period. So websites like the Exoplanet Transit database allow amateur astronomers like us to contribute our data to help verify things like the planet's orbital period, for example. So changes in the long term can indicate another planet might be tugging in a different orbit, like I said before. Now, for WASP 39b, there has been no indication of other planets just yet, but we were able to determine its orbital period of 4 days, making it extremely close to its host star at only 0.0486 AU. So for reference, Earth is at 1 AU, so it's much closer and much hotter. So far we know it's larger yet lighter than Jupiter, making its density very low. We know it's very close to its host star, meaning it's likely very hot. So far everything makes sense. Since it's so hot, it causes these gases to inflate, hence the larger radius than Jupiter, even with less mass. So we even have an idea that's likely made from these lighter components like hydrogen or helium. But in order to be confident with these predictions, we need to use transit spectroscopy like mentioned before. So I didn't choose WASP 39b for no reason. Its large size, close orbit, and inflated atmosphere make it an amazing candidate for exoplanet science. This allowed James Webb to perform transit spectroscopy for multiple orbits, really building up that signal-to-noise ratio. Now this allowed for the first full broadband spectrum of an exoplanet. So as you can see here, we actually detect things like potassium, water, carbon dioxide, and more from millions of miles away. But to give you an idea of just how much better this is, you can see in purple there the measurements made from both HST and Spitzer, where the blue ones are just the James Webb ones being added on top. So before this, we had a very tiny idea of what was going on in this atmosphere. And now with James Webb, we can actually study and determine the individual components in the atmosphere and things like that. So with all this information these techniques have given us, we know its size, mass, density, the length of its ear, we know it's hot, we even know its atmospheric components. So though this is a more ideal target, James Webb has really transformed the field of exoplanet science. In fact, this detection of hydrogen sulfide and sulfur dioxide is our very first strong evidence of photochemistry occurring in an exoplanet atmosphere. So the ability to detect these extremely tiny interactions from a distance of 700 light years away is astonishing to me. For anyone who doesn't know the size of a light year, that's 7 quadrillion kilometers away almost. So this is one of the many things that gives me hope that we will hopefully find life on exoplanets in our lifetime. And since there's actually no secondary transit data available for WASP-39b, this is the perfect opportunity to talk about one of our best bets for finding life in the cosmos, the TRAPPIST-1 system. So this is a system of 7 known planets that are all roughly Earth-sized. Now, 3 of these 7 planets are in the habitable zone, meaning they can theoretically host liquid water on the surface. Now, as you can see in the image, since the star is much cooler and smaller, all the planets orbit well within that of Mercury, the Sun's closest star. Now we do have transmission spectra for the closer planets from James Webb because they transit more often. Fortunately, due to the larger orbital periods as they're farther away, we don't yet have spectra from James Webb for the 3 in the habitable zone, TRAPPIST E, F, and G. But shown here, the yellow data points are the spectra from Hubble. And the purple behind it is actually a simulated spectra for if these planets were more puffy gas-like planets like Neptune. So these Hubble results tell me 2 things. One is that they're likely rocky worlds like Earth, not gassy Neptune-like. And the second thing is that their atmospheres are likely thinner than Hubble could measure, which is expected of an Earth-like planet at this distance. So this makes me super excited about what James Webb could theoretically uncover about these planets with its amazing sensitivity, especially for TRAPPIST-1e, which is looking to be the most promising exoplanet at the moment. So now that I've hopefully convinced you that James Webb is awesome for exoplanet science and shown you some of the methods we use to study these planets, I wanted to end off by talking about how amateur astronomers like us can contribute to the field. So while space telescopes like James Webb provide unparalleled sensitivity, ground-based observatories remain essential, especially for monitoring exoplanet transits in the long term, like I mentioned before with the Exoplanet Transit Database. For some reference, at the cost of $10 billion and an expected operation of 20 years on the bright side for James Webb, the cost per hour is over $50,000. So you better make sure that you're pointing at the exact right dip in light at the exact right time. This is why long-term monitoring by amateur astronomers like us is so helpful. Now, in order to help, I've developed a set of instructions as well as code to help capture and process these events. And it's catered to AICO, but you can definitely use your own smaller telescope for capturing the transit. So the last thing I'll walk you through is an overview of essentially how you can do this. So when choosing a potential target, there are really 5 main things you want to consider. So the first thing is clear skies. So when trying to detect a dip in brightness of 1% or less, a single cloud can make this impossible. So this is essential. But once you've found a clear night, the second thing you want is a bright and small star. So the smaller and brighter the host star, the more of the star's light the transiting planet will block. This makes it easier to pick out that transit from the noise, hopefully making it more than 1% of a dip if you're lucky. Now the third thing is a hot Jupiter. And what I mean by this is you want a large planet that's orbiting close to its host star, as these often end up being hot Jupiters. And as I said before, these are really the planets that we find the most, and this is really the reason why. The fourth thing you want is a short transit. So if you're looking for a completely clear window of weather, the shorter the transit, the more likely your chances of success. And I've made this mistake many times before, trying to capture a super long transit only to get clouded out and have to throw the data out. But the last thing you want is a high altitude. And this allows you to look through less of the atmosphere, as well as avoid any increase in light pollution that might happen around the horizon. And you especially don't want your planet dipping below the horizon at the end of your transit, which has also happened to me. So a wonderful resource for choosing your transit is the Exoplanet Transit Database, which is now held in a website called VeraAstro. So given a specific date and location, it will tell you all the potential exoplanet transits that you can potentially capture. So this is a random day I chose to show you, but if I were trying to capture a transit this day, the first things I would look at are these 3 columns. So I want a short duration, I want a low Vmag, which actually means a brighter star, and I want the largest transit depth that we can find. So the first 2 good options you might come across are these 2, and they're both great, but if you keep looking, you might come across this one. I like this one because it's a bright star, it's a short duration, and most importantly, the larger transit depth. It's very hard to pick out that smaller transit depth out of the noise. So then I'll look over here to make sure it doesn't occur too late and that all three of the numbers below there, the time there, are above 20, because we do not want it to drop below 20 degrees above the horizon, or else we'll start to get more light pollution in our way. So this is a great candidate if you're going to find if you're trying to capture an exoplanet transit this night. Once you captured your transit, you need to process this data. So, like every astronomy image, the first two things you do is a flattened bias correction. So for anyone who doesn't know what these are, a bias image is taken with the telescope shutter closed and the shortest exposure time possible. So these are used to correct for things like hot pixels by subtracting them from your images. Now, flat images are made by taking images of a uniformly lit surface, which is actually a telescope dome at AICO. These are used to correct for optical imperfections like the donuts you can see all over the flat image there, for example. Now, this correction is done by dividing instead of subtracting like the bias image. Now, the third thing is cosmic ray correction. So these are very tiny high energy particles that hit your camera and appear as tiny hot pixels or stars. Algorithms like LA Cosmic can distinguish between a cosmic ray and a star and remove them so they don't interfere with your brightness measurements. But once you've done that, you're going to do something called background subtraction. So by making a 2D model of the brightness in your image without including any of the stars that you can resolve, you can then subtract this from your images to get a better idea of the actual brightness from your stars. So in a city like Toronto, you're picking up much more than just the star's brightness. So background subtraction is crucial to remove the city lights, for example. The next step you'll do is align the stars in all your images. So by doing this, you can refer to a single pixel location in all these images, and it allows you to also do the next step, which is stacking your images. So like stacking images allows you to further remove this noise at the expense of less total images, meaning less temporal resolution. But like I said before, when trying to extract a dip of less than 1% from this noise, the less noise you have, the better. So sometimes this is a great step. But once stacked, you can take each of these images and perform what's called an aperture test. So this means creating a circle around your star and summing the total pixel values. So as you increase the circle size and make a plot, it allows you to determine the optimal circle size that will capture your star's brightness without the background noise. While doing this to your transit star, you should actually do the same to a few comparison stars that we'll be using in a later step. Now, I actually like to do a second type of background subtraction called annulus background subtraction next. So the idea with this one is that you create a ring or donut around the aperture that you chose for each of your stars, and use this ring to get a measurement of the average brightness around your star. And then you can take this average background brightness and subtract it from your value that you summed up inside of the aperture. This is another way of essentially subtracting and getting rid of that last little leftover bit of noise that you didn't get in the last background subtraction. So at this point, if you plot the total pixel value or your star's brightness for your transit and comparison stars, you see something that looks like the plot on the left there. Here's where we use those comparison stars. You know these stars are millions of miles apart and have nothing in common, so the dips in brightness that are occurring at the same time must be caused by Earth's atmosphere. So we take advantage of this, and by dividing the transit star by a comparison star, it actually removes this noise, and it leaves us with the transit curve shown there on the right. So if you're like me, it may have taken you a couple tries to get a good transit. So the one on the far right, you can see it's impossible to pick out. So this is a transit of less than 0.5% dip in brightness, where the transit on the left is actually not even an exoplanet. It's something called a brown dwarf. But it's transits like this where you really need those space telescopes that avoid you looking through the Earth's atmosphere. But now in the middle, you can see that sweet spot where this is still a planet. It's not what's called a brown dwarf, but it's large enough that you can really capture that dip in brightness. And of course, it's another hot Jupiter, which is why we find those the most. But two trends I want you to notice here is that if you're trying to capture a good planet, on the good side, you'll see the brown dwarf has a much smaller host star, where if you look to the right, it has a much larger host star. And then if you look at the brown dwarf again, its size is much larger than planet on the right. So smaller host star and bigger planet equals good transit. Now, last thing I'm going to show you is a QR code for anyone wanting to access my exoplanet transit guide. So this will bring you to my website where I have uploaded it. And this is essentially a complete guide that gives you instructions for everything from capturing, processing, and then once you process this transit, what can you extract from that in terms of information? But now I will pass it back over to Elena.
Thanks, Aiden. Great to see you. Or as I say, excellent talk. The exoplanets are a lot of fun, and of course, there's a lot of questions we could ask about exoplanets for sure. I had someone the other day ask me if an astronaut did travel to an exoplanet and died, would they leave behind an exoskeleton? But we won't make you answer that. We've got a few questions coming your way over from YouTube. We'll see how much we have time for. Um, Actually, the first one looks like it's from actually, let's go ahead and include the comment before that as a question as well. So we had a comment from Zachariah about their friend participated in the discovery of the TRAPPIST system. So I thought I would ask you, are there any more details you'd like to share about that TRAPPIST system and how it works in terms of its exoplanet discoveries?
Yeah, so there's 7 total planets in the TRAPPIST system, and it's probably the most exciting system to me. Unfortunately, like I said, only 3 of those are in the habitable zone. But if you do look, we do have a lot of data on the 2 that are closer, which I think is super exciting. But they are all rocky planets, which is great. And I believe some of them were actually found through the transit timing method, if I'm not mistaken. Uh,
I'm not
Transit
sure.
timing
That's maybe one to
variation.
look up.
I think so, but most of them have found through the actual transit method.
Excellent. Well, the transit method is, as you said before, probably one of the most popular, if not the most popular. I'm not sure which transit method is currently in the lead for number of exoplanets. But yeah, very exciting stuff. Let's see what else questions we have from YouTube. All right, people, send your questions in if you've got them. Looks like we have another comment slash question from Eric Briggs. I have not been successful in exo asteroid occultations so far. I think it's because I don't usually auto guide. Have you ever tried to image exo asteroids?
So I think that's a couple generations away. So the first thing we can hopefully do is an exoplanet. Maybe the generation after me will be able to do exomoons, but exo asteroids is really stretching those capabilities of our telescopes. We can barely directly image exoplanets at the moment. The only ones that are like 10 times the size of Jupiter. So I don't know if we will be able to do exo asteroids anytime soon, but hopefully within our lifetime.
I agree. I think it would be really exciting. Of course, direct imaging is just near magic when you see it, but really, really hard to do. And I forget what is the current smallest exoplanet that we found yet. I know we've gotten to Earth size. Do you know what the smallest one is?
I don't know the smallest, but I do know we've gotten slightly smaller than Earth, so it gives me hope for Earth-sized exoplanets.
Yeah, so if we were to look for other Earths, in theory, under the right circumstances, we might be able to find them. And of course, as you say, the TRAPPIST one had several interesting candidates. So
Mhm.
Earth or Earth adjacent, I'm not sure that we could get down to Mercury's, but if we're looking at asteroids and things, you'd have to get much, much smaller around another star.
Mhm. Yeah, exactly.
Oh, and actually, we did get a clarification. Eric Briggs was actually trying exoplanets. So, um,
Mhm.
so yes. And if you are imaging exoplanets with a setup like the one that you have behind you, is there any extra tips you would give to folks? Of course, using a large 1 meter telescope like the Alan A. Carswell Observatory has auto guide and a lot of features. For something like your scope back there. Do you have any other tips you might add?
So a scope like this one, unfortunately, it doesn't have any like tracking. A Dobsonian doesn't have any tracking capabilities. So my actual next project was going to be trying to add star tracking capabilities to this, so I can capture those transits. But it's not really about the size of your telescope. It's more how precisely can it track that star. So you need like an equatorial mount or really capable alt as like the one at AICO. But I think you definitely want to do sometimes you can get away with not doing both background subtractions at AICO. So if you don't have a 1 meter telescope, you definitely are going to have to beat down that data more because you don't have that increased signal to noise from the 1 meter aperture.
Yeah, absolutely. And of course, I will just say that if you do have the smaller scope with less accurate tracking, things like variable stars might be a little bit better because they will have bigger dips and be easier to follow. Um, and I know that there are some RASC members on the variable star track, shall I say? We have I think we have a time for a few more questions. So good to see a few rolling in. This is actually, I think, going to be one right up your alley. It's about the software. So this is from Zachariah. Any idea about the software used for image processing to discover the exoplanet? And I know, of course, we used Python. Um, but do you want to maybe just talk about what's in the software a little bit?
Yeah. So I guess I could sort of go back to the slide there on my screen. I don't know if you want to. Is it possible to show the screen? Yeah, so like as you can see, all of these steps are mostly done with Python. So I use AstroPy. It's a dedicated Python library that's made for astronomy image processing. So it actually has tools for pretty much all of these steps. In fact, every step there on the screen it has a tool for. Even has it for stacking and it has this tool for the aperture test. So AstroPy is your go-to Python library if you want to process variable stars or exoplanet data.
Yeah, absolutely. And AstroPy is super, super valuable. I will say that some people like to use AstroPy with PyRAF, which is Python plus IRAF. Most places have switched from IRAF to PyRAF to just AstroPy. But if you like having a little more control over some aspects, using your old 32-bit compiling IRAF will still work. So if you're a little more old school, you like to run sed op grep in your command line, IRAF old school 32-bit might be more your speed. But if you're looking at running it on Colab or a cloud notebook, then you probably want to go more for the PyRef. Now that's not a question, so
Mhm.
we'll go ahead and take last questions. And in the meantime, I'm just going to ask you the usual question, which is, so right now, do you have a favorite exoplanet?
Yeah, I think it's got to be TRAPPIST-1e. It's I think our best bet for hopefully finding like actual life on an exoplanet. I know there's a lot like microbial life. There's a lot of planets that have the potential for that. But in terms of like real I don't know, a way you picture like an Earth-like planet, if that's what you're looking for, then I think TRAPPIST-1e is our hopefully best bet. And I think it mostly gives me more motivation because we don't have the data yet. So it gives me, the data hasn't told me and we're wrong yet. So I hope it comes back and it's tells us it's Earth-like.
Yeah, or at least an interesting atmosphere, because this is one, as I recall, you said there was no atmospheric data for yet, or very little atmospheric data.
Very, it's not significant enough because they're having issues with there's star spots and because it's a further out transit, so it doesn't transit quite often. It's basically not significant enough to show any really atmospheric signs. So we need more transits to occur with less star spots.
Yeah, and of course, those star spots are also going to be in play on our own sun in a smaller fashion, with the solar maximum and the aurora. So if people are interested in seeing star spots, they're very hard to see on exoplanet systems, but they will be easy to see on our own star for a little while longer. And actually, I would just say that in terms of the star spot problem on exoplanets, just last question, I suppose, rounding off if we don't get any more from chats. Um, what's the difference in the star spot problem for different types of stars?
Uh, that's a great question. That's a little bit out of my expertise, but I know that, for example, the TRAPPIST-1 system some of the closer planets are actually great targets for that reason because they're great targets for actually seeing how does that solar maximum, like those cosmic rays coming in strip a planet of its atmosphere. So that's another reason why TRAPPIST-1 is such like an exoplanet scientist dream, is because it also has great planets for studying how that effect happens. But I'm not too sure about what stars would be more active versus less active in order to strip them from their atmosphere.
Well, that's I think that's probably we're rounding off all the questions we have time for. I'll just give a quick peek over onto the YouTube chat. It looks like that's all that people have posted live. So if folks would like to leave other questions, they can do it in the YouTube chat after the recording is done. And of course, we do have to round off to transfer to our next area. So thank you once again to our wonderful speaker, Aiden, for joining us again in a truly, truly excellent talk, exceptional, one might say. And we will go ahead and transfer off for our last shift of the evening. I'm going to hand over to the president of the Toronto Centre RASC, Scott Masterton, to finish off the evening. Over to you, Scott.
Thank you, Elena, and thank you to everyone for tuning in tonight. Tonight we have some announcements, and they'll probably be of interest. Of course, I want to describe what we did tonight and what we do in a couple of weeks. So tonight was our speakers night, and that's of course online. We draw on speakers from all over the country, and our other night is the recreational astronomy night, where our members educate and speak to you about projects of their interest. And of course, during the chat, as you've seen, you can say hi or ask questions, and that will we'd like to hear from you while you're watching. The next speakers night is March 19th, and that will be Alex Jude of York University. Title of his talk is An Educational Guide to the Quail Telescope, and you can log in at the indicated URL. Recreational Astronomy Night, our next Recreational Astronomy Night, March 5th, and we will have the sky this month, and you'll get the lowdown on the next 30 days of things to see in the sky. That'll be Dennis Gray. Frank Dempsey, with his current visual observing project, will entertain us, and Jeff Booth and Tony Horvatin will talk about the Aurora Borealis. The Carswell Observatory tours occur every Wednesday evening, and I enjoyed that the last time we had a RAN, and it's very interesting. You'll get to see two telescopes. The older one, the Carswell, that has been refurbished from several years ago, and a new Planewave 1-meter telescope. Very interesting. The DDO has various astronomy programs. Here's Sunday sun gazing, February 23rd, online, and you can sign up at the indicated location. The DDO also has a Space Action Craters and Comets, Saturday, March 8th, during the March break. So you kids that are away from school for that time, here's something you can do and learn about astronomy. Another talk on March 12th is Out of This World, the Solar System, at the David Dunlap Observatory. Registration is required, of course. And another Sun Fun, March 15th, 10 a.m. to noon, at the DDO. Another March break activity. DDO Astronomy Night, Family Night, Constellations Connecting the Dots, another entertaining evening at the DDO. Families will see a presentation of celestial activities, and you can sign up at rascto.ca. Astronomy Speakers Night for March 22nd, is Dr. John Moores of York University, Daydreaming in the Solar System, Exploring the Planets with Our Five Senses. Again, you may sign up for that and for a DDO talk. The Carr Astronomical Observatory is our observatory where we have telescopes, and we do talks, and the operations are back to pre-pandemic conditions. The road is plowed, and so we have access during the winter months. Go to the online CAO bookings page for details. And when you're there, you can have a look at our roll-off roof observatory. This is a picture of the viewing space. The roof rolls back, and our 14-inch telescope can view the sky, and you can see that there's plenty of space for other telescopes in there as well. This is the warm room where the telescopes are controlled. You can stay toasty in the cold weather or avoid the mosquitoes in the summertime. We run on renewable volunteer energy. If you are an RASC member and are interested in helping us, if you have free time, we're looking for volunteers all the time. Contact the volunteer coordinator. And of course, you have to be a member, and you can join at the national office, mempub@rasc.ca. Sign up online. And have a good night. Thank you for tuning in.